Welcome to the first class of the Introduction to Quantum Computing and Information. As I already explained during the orientation, my name is Taehyun Kim, and then my contact information is here. And these are the list of TAs for this class. So feel free to contact either me or the TA for the class details. And then this is the allocation of the grades. So yeah, before the COVID-19, I generally don't put a lot of weight on the homework, but because a lot of things should be also done remotely, so I increased the proportion of the homework, and then these are the proportion of the um, midterm exams and then final exam, and then these are the schedules, and then we already fixed this schedule. So don't make any other appointment or plan during this time. And this is the just a list of the textbook. So this is the tentative schedule for this semester. Um, I will try to keep follow this tentative schedule as much as possible. But in the worst case, which actually happened in the last year, I had a severe delay in recording the lecture videos. So I hope that the same situation won't repeat this semester. But again, in the worst case, if I have any delay, then because we already fixed the midterm exam schedule and the final exam schedule. So if my recording of the lectures are being delayed, then the coverage of the midterm exam will be adjusted according to my progress as well. So my goal is to cover everything up to quantum algorithm at least before the midterm exam, but in the worst case, it might be covered only up to here or even up to here. Yeah, so let's see how it goes, and then um, make sure I just want to emphasize one more time that the this class has a prerequisite for the linear algebra. So I will still spend almost 3 weeks to review the uh, give you an overview of the linear algebra, but that does not mean that you can take this class without knowing about the linear algebra. I will simply assume that you have enough background for the linear algebra, and then if you don't have enough background, then I'm actually quite concerned that you might not survive in this class. So if you don't have any background, then maybe you should consider taking this class in the next semester rather than this semester. So yeah, um, during these 3 weeks, um, the review of the linear algebra will go as something like um, because in the quantum mechanics, we are using a little bit different convention for the linear algebra. So yeah, the goal of these 3 weeks is to make you feel kind of comfortable with the new notation for the linear algebra. And then I will try to give some brief introduction to the quantum mechanics, but of course, quantum mechanics by itself is a vast area, so I cannot cover. Yeah, even with one semester of class, I cannot cover everything about the quantum mechanics. But the goal of this class is not to teach the quantum mechanics, but we are going to use some concepts of the quantum mechanics. So I will just give a very brief introduction for the quantum mechanics, and then we will then jump into the quantum circuit, and then I will give a lot of different examples for the quantum circuit, and then based on that knowledge, yeah, we can now start to introduce about the quantum algorithm, and there are also many varieties of the quantum algorithms, and then of course I cannot cover everything, but I will just um, um, explain some of the representative quantum algorithm. And then surprisingly, most of the quantum algorithms are just a variation of these algorithms, which is also the limitation of the quantum algorithm nowadays. We need more useful and then more powerful quantum algorithm for the quantum computing. And once it is done, then I will also introduce about some of the quantum computing service which is commercially available nowadays. And now I might touch some of the important topics in the quantum information. So yeah, even though the name of this class is quantum computing, but still it has quantum information. And then one of the important topic in the quantum information is quantum cryptography. And then quantum error correction is basically related to the quantum computing. So, but it is advanced topic, so I will postpone up to 11th week. And while I'm introducing the quantum error correction code, I will also do some of the review of the classical computation theory. And for the rest of the semester, I will spend some time on the I will spend time to introduce the advanced concept in the quantum information theory. And then finally, yeah, in the last almost the last week of the semester, I will give some overview of the or comparison or connection between the quantum information and the classical information theory. Okay, so let's begin our first lecture. As all other linear algebra class starts, we will also start with the concept of the linear vector space. And then linear vector space is defined as a collection of the object, which is called as vector. And this vector should should have some of the well-defined operations. And then two of the most important operations are the addition of the vector and then multiplication of the scalars on the vectors. And then I'm sure that you are very familiar with this concept. And then still, if you have any of the trouble, then probably the easiest and the well-known vector example is the arrow in the 2D space or 3D space. So let's say that we have some kind of 3D space, and then three-dimensional space, maybe these are the bases, and then we might have some vectors like here. And then in this case, we will call all of these arrows as the vector, and then we will use a notation, something called as something looking like this one. And then I will introduce this notation more carefully in the next page, but we basically use this notation instead of notation which you are more familiar with. So for the vector, you are probably more familiar with the shape of this matrix-like format, and then this is generally called as the um, um, column vector. So yeah, in the typical case, you would say that this vector is you might just say that well, that is the v arrow, and then they are defined as the x component. And then yeah, if I define this one as x y axis and z axis, then you will have some projection on each of the axis, and then you would write down each of the component on this part. So they will be composed of v sub x, v sub y, and v sub z. So these are probably more familiar notation. But now, eventually, well, this is specifically defined for the three-dimensional space. And then, of course, this space can be expanded to the n dimension, which we cannot easily imagine in our brain, but we know that it can be always generalized to larger dimensions. So that's what we are going to do. And then in that case, probably this kind of arrow notation is not very good. Yeah, so that's why we are using more abstract shape of the vector, something like this one. And then yeah, we will spend a lot of time just trying to introduce the this notation in the next several lectures. So yeah, this addition looks like two vectors are added, and then that is exactly the same like if I have addition on another vector w like this, and then the summation will be just the summation of these two vectors. So yeah, it might represent something like this vector, and then multiplication, and then you know that if we multiply 2 for this vector, then it will become 2v, and then that means that its length will be increased by factor of 2. Yeah, so these are well-defined operation. So you probably have no problem in imagining this one. But more important, and then which might be easily ignored, is the requirement for the closure. Closure means that whenever we do some kind of audition, then the result of the audition still should remain inside this space. So you might think that, well, in three-dimensional space, um, if we add any vectors, how can the vector go somewhere else? So yeah, for the typical situation, you might not imagine such kind of situation. But let's say that if we define that our vector space is limited within two-dimensional space, something like this one, and moreover, let's say that our vector stays only inside this kind of circle with the radius of 1. In that case, if we have two vectors, something like this one, then their addition, the added result will still remain inside this boundary. But if you have additional vector and another vector like this one, then each of them belongs to the vector space, but addition of that, these two vector will be outside the boundary. So in that case, it cannot be considered as a good linear vector space. So yeah, closure is one of the most important requirements for the vector space. And then there are also a lot of different requirements. And then all of these, yeah. So for example, yeah, this is the um, this means that distributive property should be valid for either scalar multiplication. Well, yeah, so it should be distributive over the vector, or it should be distributive over the scalar. So yeah, these are very easy concept if you imagine about the three-dimensional vector space. And then also because a scalar is almost like a real number or whatever number you are more familiar with. So you know that they are associative, which means that whether we multiply this scalar to the vector first and then multiply this scalar later, or we can first multiply these two scalar first and then multiply the result of the scalar multiplication to the vector. So these are well-known concepts. And then if you imagine everything in terms of this three-dimensional vector, then everything makes sense, right? But what we are doing is the main reason we are listing those obvious results is by defining only these results, we can be free from the concept of the three-dimensional space. We can generalize everything to the n-dimensional space with this definition. And then again, yeah, this is the addition of the vectors should be commutative, which means that their order of the addition should not affect the result of the addition. And then generally, if these are the number, we know that addition is always associative. But what we are also emphasizing here is that the addition of the vectors should be associative, which means that they're the whether we add these two two vectors first and then add this one later, or we can change the order of the addition, and then the final result should be identical. And this might be still too obvious, but if we don't have well-defined null vector inside the vector space, then we will have a lot of trouble. So yeah, make sure that you should yeah, once you are given some kind of definition for the linear vector space, you should always check that whether there is whether null vector can be well defined inside that vector space. And then finally, once we have the concept of the null vector, then we can also define something called as inverse of the addition. So if we have the vector, then we can always well-defined linear vector space should also have the inverse of the corresponding vector. And then the inverse is defined as if you add these two vectors together, then it will go back to, it will produce the null vector. So these again, these concepts are very well-known concepts in the three-dimensional space. But yeah, again, we are making an abstract math, and then we will only discuss everything based on the abstract math. And yeah, and then yeah, again, this might look very obvious, but without this definition, you might have some trouble in expanding the concept of the linear vector space. So these are 8 requirements for the definition of the linear vector space. And yeah, another thing, well, when I'm talking about the multiplication of the scalar on the vector, yeah, we had this scalar number, and then these numbers are generally called as a field, and then yeah, field, yeah, well, the word field might be used in different area in different with different meaning, but in linear algebra, field has very well defined meaning, and then the everything we are multiplying here to the number we can multiply to the vector is called as a field, and then we say that the field over which a field is defined over the vector space. And again, yeah, concept of the scalar is very simple. Yeah, probably most of the numbers you are just using are scalar, and then sometimes in um, um, in very careful definition, scalar is different from the might be different from the field, but in most of case they can be considered as almost identical. So at least for the level of this class. So in this class, I will just use the scalar or the field exchangeably, but in the worst case, there you might have some distinction. But yeah, for the time being, you can just ignore the distinction between those two concepts. But the reason I'm emphasizing about the field is every linear algebra class, not every, but most of the first year linear algebra class or the first semester of the linear algebra class, you are not you are only considering the field. Uh, you are only considering the case when the field is real number. So in the specifically, if you are familiar with the concept of the three-dimensional space, then every number used in this space are real. So yeah, there is no reason why you have to consider the complex number. But in the quantum mechanics, all the fields are basically complex number. Well, complex number means that it will include both real and imaginary numbers. So yeah, of course, we also use the real number inside the quantum mechanics. But as you are calculating things, then you will realize that you need the concept of the complex number. So the biggest difference between the most of the linear algebra and then the linear algebra used in quantum mechanics is that quantum mechanics use the complex field, and then we also called it as a complex vector space. So that's the biggest difference, and then you will appreciate why we need such kind of concept. In the previous page, what we did was defining the linear vector space. But in this page, what I'm going to list is the result of that definition. So yeah, if you just look at this result, then you might think that what's the difference, whether it should be zero vector should be unique. Is that the property or is that the definition? And then based on all those 8 definitions which are listed in the previous page, then if you combine those results, then you can actually prove that the null vector should be unique. Another property you can immediately derive is that if you multiply zero value of the scalar, then you will end up with the null vector. And another thing is that the inverse of the vector can be also obtained by just multiplying -1 to the original vector. And finally, you you can you can also prove that the inverse of the some vector is unique, and that these properties might be very um, is obvious if you think about everything in terms of the three-dimensional space. But if you forget about the three-dimensional space and then only consider the definitions given in the previous page, then there is no reason why all of these properties should be valid. And then, but again, still based on all those definitions, you should be able to prove these properties or derive these properties, and then that will be left as homework for you, because I just want, these are probably very easy proof, but I want to make sure that you are familiar with the concept of the linear algebra. So yeah, again, this proof of this will be left as homework. And then another thing I want to give you an overview is the cat and the bra. So in the previous page, I mentioned that cat can be somehow considered as the, if we have a cat, then it is very similar to the concept of the column vector. And then let's say that we might have every ABC, and then we also have, and then and we call the vector shaped in this one as a cat vector, and another shape is reversed shape, something like this one. And then in this case, this is exactly same, or that this one corresponds to the row vector, something like this one. So yeah, let's say that this is W, then this can be D, E, F, and then we know that when we are given any of the, and this is called as a column vector, and this is called as a row vector. But in some other cases, this can be also considered as one of the shape of the matrix, and this one can be also considered as a matrix. And then we also can define the multiplication of a two matrix. And in this case, the most familiar multiplication of the two of the matrix is something like this one. So this will be a well-known well-known multiplication, and then you know that the result is AD plus BE plus CF. And for this case, we might either consider this one as a multiplication of two matrices, or you might consider that this is the inner product of two vectors, right? So in this case, if we might also have exactly the same concept of the inner product with this bra vector and the cap vector. And then if you consider that this one corresponds to bra vector, something like this one, and this one, this one corresponds to cat vector, then this multiplication just looks like the bra and cat vector, just combining these two. And if we calculate this value, then this exactly represent this inner product. And then I will give you more concrete example in the next page. And then, but yeah, what I want to emphasize here is that this row vector corresponds to bra vector, or yeah, I should say the other way. Yeah, so the bra vector. Yeah, if you are not familiar with the concept of the bra vector, then you can just map that the bra vector represent the row vector, and then the cat vector represent the column vector. Then everything will just looks like regular linear algebra. And then again, now you might wonder why they are called as a bra and cat. And if you see the inner product of these two vectors, then the reason becomes obvious, because the first one is called as bra, and then the second one is called as cat. And then if I add C here, then it is bracket. And then that bracket also makes sense because the shape of this one is really look like a bracket. So that's where the name of the bra and cat come from. Yeah, so this is this kind of notation was introduced by Paul Dirac, which who was the famous physicist. And then yeah, nowadays in quantum mechanics, everybody uses this bracket notation. So you should just get familiar, get yourself familiar with the concept of the bra and cat vector. And then, yeah, now, yeah, let's move on to some of the different vector space. Yeah, it is obvious that all these properties and then every definition in the previous page makes sense if you consider them as some arrows in the three-dimensional vector space. But three-dimensional vectors, the vectors in the three-dimensional space are not the only vector space. Actually, there are a lot of different types of the vector space we can imagine. For example, yeah, one is the 2x2 matrix, and then another is function defined in some of the interval, and moreover, some of the periodic function inside some within some interval is also they make very good vector space. And then let me give you some example of these cases. So when we prove that something is a good vector space, there are two things we have to prove. The first is whether it has a well-defined addition of vector. And two is the scalar multiplication. And whether these are closed, meaning that the result of the addition where the scalar multiplication still belongs to the original vector space. And then one of the example was a 2x2 matrix. And it is obvious that even though we are more familiar with the concept of these column vectors, they don't really need to be vectors. These kind of column vector style, they can be either, they can be something like A, B, C, D, and then we are familiar with the X, Y, Z, alpha, something like that. Then we know that everything, the result of the summation will still belong to the original 2x2 matrix. So there is no reason why this shouldn't be a good vector. And then again, you can also multiply any of the 2x2 matrix with some value like anything x, and then they will still be xa, xb, and blah blah. And then this is still 2x2 matrix. So it is closed under these two operations. And then you should still check whether this 2x2 matrix satisfy every requirement, every property, or every requirement for the definition of the linear vector space. And then you can easily check that. Another vector space I mentioned was the function function defined over L. Yeah, so let's say that 0 and L, and then we might have some function, something like this one, and let's call this one as f1, and we might have another function from 0 to L, and yeah, let's say this one is something like this one. Then let's call this one as f2 vector. Then we know that from the definition of this, f1 plus f2. I don't like this these two functions. So let's say that I have something like this one, and then another one is something like this one. This will be easier to draw. Then I can say that we have 0 to L, and then we might have something like this one. And this is the result of the summation. And we know that this one still belongs to the definition of the function, which is defined in the interval between 0 and L. So the addition is closed. And also, if we multiply some scalar value like 2 or 3 to this f1 or f2, then they will be just increased by a factor of 2 or a factor of 3, or whatever we multiply, they will still the result of the multiplication will still remain as a function which is defined between the interval from 0 to L. So function defined between function defined in the interval from 0 to L is a very good linear vector space. Another vector space example is a periodic function. So let's say that we have some kind of periodic function. Maybe this is one of the good periodic function, and another is let's say that this might be also another good periodic function. So this is the period L, 0 and L and 2L, 2L. Then if we add these together, then the result will be still periodic, something like let's say I don't know, maybe yes, this might some goes like this one. But the point is, if this is f1 and this is f2, then f1 plus f2 will still remain as the result will be still periodic between periodic function with the period of L. And then whether we multiply some scalar value to f1 or the whatever we do, the result will still remain inside the our defined linear vector space. The next important concept is the linearly independent, and then maybe linearly independent, dependence and the linear independence can be explained by using some simple example. For example, let's assume that we are considering two-dimensional space. Yeah, so something like this space, and then in this space, let's assume that we have two vectors. Yeah, this is one vector and another vector is parallel to this one, and the length is twice. So in this case, let's call this one as V and this one as W. Then we know that the W is twice the V. So in other words, we can always find some kind of combination which is, well, let's say, well, we might say that this is the V equals 0. And the question is whether we can find any linear combination of these two vectors, and then whether we can find some combination of the linear combination, and then whether all of these coefficients are 0 or not. And then if we can to satisfy this this kind of equation with the null vector, and then the only option we can find this equality with the null vector is only when all the coefficients are 0, then they are called as independent. However, for this case, we can find some combination with 1 and -2, which are all non-zero. So in this case, V and W and V are dependent. So if they are parallel, then they are dependent. So this is an example of the dependent vector. Now, let's say that we have an additional vector, something like, now this is now called as a V, and well, yeah, let's use different notation. And this is X vector, and then this is the Y vector. So in this case, we cannot find any combination of X and Y, which will make which will become and then for this kind of two vectors, we cannot find any combination, any linear combination of X and Y, which will make the total of the linear combination equals to zero, zero vector. So in this case, because the only option we can find to satisfy this this equality is only when both of these coefficients are 0. So in this case, X and Y are called as independent. So now the question is whether, yeah, in the two-dimensional space, yeah, if we have two-dimensional space, yeah, in the two-dimensional space, whether we can find three independent vectors, which means that whether, yeah, for example, if I just draw three vectors, something like this one, and then let's say that yeah, this one, then if I call this V and then W and X, then whether they can be independent. And the problem is we can always once we have these two, then for this third one, we can always find some kind of combination. Yeah, so if I draw something like this one, then I know that, well, yeah, wait, yeah, yeah, so maybe I can just draw in this way and this way, then this X vector can be decomposed into the summation of this vector and then summation these two vectors. Yeah, maybe I should draw with some different color. So this one and this one. So X can be written as some kind of multiplication of W vector. Yeah, let's say that is CW, and then the value corresponding this one will be CVV. So in other words, we can always find that CWW plus CVV minus X becomes 0. And then in this case, we know that CW and CV and -1, yeah, so we can find some combination of the coefficients which are not all 0. So in this case, we know that in the two-dimensional space, there are no three independent vectors. So that now leads to the definition of the dimensions. So the definition of the dimensions of the vector space is that if the maximum number of the linearly independent vectors is n, then that defines the dimension of the vector space. So for example, for the two-dimensional space, we cannot find three independent vectors. So the maximum number of the independent vectors we can find is 2. So in this case, the dimension of the two-dimensional space is 2. Yeah, maybe I'm just making the same argument repeating, but that's how we can define the dimension of the vector space. And then depending on whether the field is real or the complex value, yeah, we have a notation for the vector space, and then if the field is real and the dimension of the space is the n dimension, then we use this notation. And if the real number is replaced by the complex number, then this is the notation for the n-dimensional complex vector field. Then, what is the dimension of the vector space composed of a 2x2 matrix? Well, it might, yeah, if you didn't see this kind of problem before, then it might be a little bit confusing. But if you think about the 2x2 matrix, let's say that this is A, B, C, D matrix, then another way we can consider is, well, this might be just can be written as A, B, C, D, and then we simply remember the mapping of the each of the components from this 2x2 matrix to this column vector, then they are kind of equivalent. So, and then we know that this one has the 4 dimensions. So the dimension of a vector space composed of 2x2 matrices is the 4. So again, the vector space doesn't need to be a real 3-dimensional vectors. It can be abstract. The concept of the vector space can be abstracted, and then it can be always generalized to any of the space which satisfy those requirements which I showed you in the beginning of the class. And this is probably one of the very important theorem. And then what it says is that if we have, if we are considering n-dimensional space, then any vector inside that n-dimensional space can be always written as a linear combination of n linearly independent vectors. And this can be easily proven. So the theorem 1 goes in the following way. So we are assuming the n-dimensional vector space. And the claim is that we can always, for any given v, vector v, we should be always find out the, and then we are assuming that there is n-dimensional, n linearly independent vectors, then we should always be always be able to find out combination of C1, C2, and Cn coefficient combination, which will satisfy this one. And to prove that this theorem is correct, we can prove that by using the contradiction. So proof by contradiction means that we deny the conclusion. So that means that we are simply assuming that we cannot find this kind of combination, which means that, yeah, so we cannot find this kind of thing. So in other words, what we can say is that if we move this v to here, then minus v cannot be 0. So by making a contradiction, or not by making the contradiction, but by denying the conclusion, then we are assuming that if we deny the conclusion, then we should not be able to find out the combination of this, which will make the total linear combination as 0. But we know that if we set everything, every coefficient to 0, even for this -1 to 0, then we should be able to find out 0. So what that means is that the only combination of these n+1 vectors, because there are n vectors, 1, 2, 3, n vectors plus 1. So total of n+1 vectors. So linear combination of n n+1 vectors becomes 0 only when all the coefficient C1 to Cn, and whatever is V in front of V becomes 0. So only when everything's are 0, then this 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 equation can be satisfied. And then in that case, what do we call about these n plus 1 vectors? They are linearly independent. Then now we have a contradiction. So we have linearly independent n plus 1 vectors. However, if we go back to the definition of the dimension of the vector space, when we call that the dimension of the this vector space is n, is only when we cannot find out n plus 1 linearly independent vector set. So by denying the conclusion, we have a contradiction that we should be still able to find out n plus 1 linearly independent vectors. So our denial of the conclusion is wrong. So by the and then we obtain the contradiction. So the only way we can satisfy we can avoid the contradiction is that we do not deny the conclusion. So that's how the proof by contradiction goes. So yeah, by using that, yeah, we should be able to find we should be able to prove that in n-dimensional vector space, we should be always decompose any of the given vectors into the linear combination of n linearly independent vectors. Now we can define the basis of the vector space, and then when we have the n-dimensional space, then that means that we should be able to find out maximum n linearly independent vectors, and then these set can are generally called as basis. And then what that means is that basis doesn't have to be unique. For example, for the two-dimensional space, yeah, if we have this might be a very good basis, but another option is yeah, this kind of thing can be another good basis. And then basis even don't have to be orthogonal to each other. So yeah, still moreover, we can find we can say that this might be also very good basis. But generally, yeah, eventually we prefer some orthonormal basis. But in principle, every independent, linearly independent vectors can be are qualified as a basis. And then in the previous page in the theorem 1, we learned that in the n-dimensional space, any arbitrary vector can be written as the linear combination of n linearly independent vectors. So that means that any arbitrary vector can be expanded as linear combination of bases. Now, yeah, we have another definition of the name, and when we have this kind of vector, then any arbitrary vector, then it can be expanded as the linear combination of the bases, and then we will obtain a lot of these coefficients, and then all of these coefficients are generally called as the component vectors. So yeah, and then I will still frequently use the um, um, terminology components or the coefficient frequently, and then whenever I say that, I actually mean the same thing. And then the components of the vectors are actually not unique, meaning that even for the same vectors, something like this vector, yeah, this vector can be written as in terms of this basis. Yeah, so for this basis, yeah, if I call this one as x base, and then this one as y base, then we have this kind of coefficient, and then this kind of coefficient. So this v vector can be written as cxx plus cyy. However, if we define another basis like let's say this one, and another one is something like this one, then we should be still able to find out the linear combination of these two. Then in this case, v will, and if I call this one as alpha, and this basis as beta, then the c probably black is not a good option in this case. Cx alpha, sorry, C alpha so C sub alpha plus C sub beta. Then in this case, C sub alpha and C sub x doesn't have to be the same. And then, yeah, of course, there is no reason why they should be the same. So if we have different bases, then the components doesn't have to be the same. On the other hand, if we have for any given basis, so if we stick to either xy basis or alpha beta basis, once we decide our one basis, then within that basis, this component value or this expansion will be unique. And then it can be also proved, this second theorem can be also proven by using the proof by contradiction. Yes, and then for simplicity, if I just use the example for the two-dimensional space, then let's assume that we have v vector, which can be expanded as the 1 and 2 vector combination. So yeah, C sub 1 and C sub 2. And assume that because we deny that the conclusion. So if we assume that this expansion is not unique, then what that means is that we should be able to find out another combination, C, let's say that Cx plus 2Cy, and then if we deny this conclusion, then that means that C1, C2 combination doesn't have to be the same as the Cx and Cy combination. But if we start with this relation, then what we can also obtain is that C1 minus Cx 1 plus C2 minus Cy 2 combination becomes 0. And then because we assume that this one and this one doesn't have to be they are not simultaneously the same to each other. So that means that at least one of them will be non-zero. And then what that means is that we should be able to find out non-zero component. Yeah, at least one of them is non-zero. And then yeah, even for the two linearly independent bases, because I assume that this is the basis, and then basis means that they are linearly independent. So even for these two linearly independent vectors, I should be able to find out combination of coefficient which is not all zero. So what that means is that this vector space cannot be two-dimensional because I should be able to find out non-zero coefficient. So now, because of that, then we obtain the contradiction. So and then the contradiction came from because the contradiction was obtained because we deny the conclusion. So by using that proof by contradiction, we should be able to prove that this theorem theorem 2 should be valid. The next topic I'm going to cover is about the inner product. And then I want to emphasize that in high school, when we first learned the linear algebra, then we generally learned about the three-dimensional space and then vectors, and then very naturally we learn about the inner product. So somehow, yeah, when I first learned the linear algebra, I didn't realize that the concept of the vector space is kind of independent of the inner product space. Of course, um, inner product by itself will be very convenient inside the linear space, but on the other end, vector space by itself doesn't need to have inner product. Yeah, so some of the vector space might not have a well-defined inner product, and then still it is valid as a vector space, because to become a vector space, all it has to satisfy are the properties which were listed in the first page of the this class. So as long as everything's are those 8 requirements are satisfied, then they are good vector space. And then up to previous page, all the properties depends on the definition of the only the definition of the vector space, and then not on the definition of the inner product. Yeah, so everything up to now was require only the concept of the vector space. Now we are adding additional property of the inner product. And then by introducing inner product, we will have more freedom in the discussion about the linear space. So so the first thing we are going to do is we will review the property of the inner product in the three-dimensional space. And then based on that result, we will generalize some of the concept, and then we will expand the concept of the inner product to more generalized n-dimensional space. So let's think about what kind of properties does the inner product has in three-dimensional space. So if we think about the three-dimensional space as shown here, then we can first think about the inner product in the three-dimensional space. Then yeah, A dot B is simply as A sub x, B sub x, plus A sub y, B sub y, plus A sub z, B sub z. Yeah, this is a well-known property. And then the first point I want to emphasize here is that the result of the inner product becomes a scalar value. And another property of the three-dimensional inner products is that they are symmetric. So it is obvious from this expansion. And then the third property is that if we calculate the inner product of the vector by itself, then yeah, that means that every component there will become simply replaced by the square of each component. And then that means that this should be either larger than 0 or equal to 0. And then it becomes equal to 0 only if a the inner product of the vector becomes 0 only if A by itself is zero vector. So that is the third property. And then the final property for the three-dimensional vectors, inner product of the three-dimensional vector is that the distributive property, or not distributive, but it should be called as a linearity. So we might consider the linear combination of some vector, and yeah, something like this linear combination. And if we take the inner product of these two vectors, A and the linear combination of these two, then the final result will be the inner product of A and B, and then A and C inner product, and then the coefficient will be still come from this one and this one. So yeah, this kind of property is called as the linearity of this inner product operation. So these are the property of the three-dimensional vector space. And then now we will generalize the concept of these to the um, more generalized n-dimensional space. Now we can generalize the what we obtained for the three-dimensional vectors, inner product of the vectors. Then the first requirement is that um, yeah, any of the inner product of two vectors are generally they will become a number. And then in this case, we also generalize the situation to the complex situation. So this number can be a complex number. And then the second generalization of this symmetry might look a little bit weird, but if you remember that all these symmetry properties were obtained when we were considering the real three-dimensional vector space. But if we generalize to the complex vector space over complex field, then this kind of symmetry might not be complete or enough. Yeah, so eventually you will realize that to satisfy all the other requirements, then it is better to have complex conjugation result when we change the order of or the role of the cat and bra. And it will become more obvious in the later and probably in the next class. And third property, which is exactly the same as the previous one. So previously we defined that we found that the inner product of the same vector should be either 0 or larger than 0. Yeah, so it should be always positive or either 0. So it is called as a positive semi-definite. And then it will become 0 only if the vector by itself is null vector. And then to satisfy this requirement, then skew symmetry is actually better than this symmetry for the complex vector space over the complex field. And the last thing is that linearity, and their shape is almost the same as the before. So yeah, the linear combination, the inner product of the vector with the linear combination will become as the linear combination of individual inner product. Yeah, so this is called as a linearity. Okay, so now we define the generalized inner product, and then definition of the inner product space is following. So again, yeah, in the previous page, we only considered the vector space, linear vector space, and now we introduce the concept of the generalized inner product. So if some vector space has the well-defined inner product, then we call that vector space as the inner product space. And then this concept is also generalized to the Hilbert space, but Hilbert space also requires some more definition. So for the time being, we will just consider this one as an inner product space. And then all the quantum mechanical calculation happens inside the inner product space. Now, with the well-defined properties of the inner product, generalized inner product, then we can consider some of the example and then whether they are qualified as a good inner product or not. Yeah, for example, first example is that for the here I'm assuming that these vectors are defined inside the three-dimensional space, but the inner product only considers the two components, and then whether this kind of definition of the inner product qualifies as a good generalized inner product, and then it might look yeah, it might satisfy many of these requirements. First, if we consider the first requirement, then because these are just three-dimensional real vectors, so the product of the real value and then addition of them will become a number. And then now we are also considering the real values, so we even don't need to we don't even need to worry about the complex conjugation problem. And then they, yeah, for this definition, they are symmetric for this one. The problem is this definition of the inner product does not satisfy this third condition, because at least it satisfies the first condition, but it does not satisfy this second condition, meaning that even if we have, let's say that a vector is something like 0, 0, 1, then the a vector a dot a becomes 0, but yeah, to satisfy this one should become 0 only when the entire vector is 0, but here a is not 0. So for this case, um, um, this third condition cannot be satisfied. So this definition of the inner product is not a good definition. Now, what about this one? This one is also good for the first case, but for the second case, if we swap, if we exchange the role of the A and B, then now the result will become different. So yeah, it is easy to see that this definition of the inner product does not satisfy this second condition. What about this one? It might look like this is not good for some reason, because this doesn't look like a regular inner product definition. However, this is actually good inner product definition based on these requirements, because it satisfies the first condition. This becomes the real number, some number, and then they are symmetric with respect to the exchange of the A and B. And moreover, this one is satisfied if we replace this B with A, and then everything will be just the square of each component. And then this second condition is also valid, because if any of these A components, one of these three components are not 0, then this one won't become 0. And then finally, yeah, if you plug into this result, this definition into this requirement, then you can easily find out that this one will satisfy the linearity. And finally, for this one also looks very similar to this one. So you might think that the definition of this inner product might also satisfy all these four components, and unfortunately not. And then the first three requirements are satisfied even for this definition. But for the first condition, this one requires linearity. But if you have this kind of example, then you won't have the linearity condition. So among these four, only the third one is good inner product, and then all the others are not a good definition for the inner product. And then among these, one of the reasons I'm just showing these four different examples is inner product doesn't have to be the typical shape of the typical. It doesn't have to be the same shape as we are familiar with. So it doesn't have to follow the definition of the three-dimensional inner product definition. And then yeah, as long as you satisfy these four conditions, then any other shape of the inner product are still very good, and they are valid inner product. Okay, looks like I probably should stop here, and then I will continue from the properties of the inner product in the next class.